So I have to do this setting also, so we have a minute more. So I never ended up pursuing our idea of get together, but I got an email. I think I not read it carefully again, where department is doing the picnic. So that's also so now I feel less guilty. And I think Michael's your batch, right? I think if you were to graduate this semester, you probably never had a gathering, right? So yeah, there's a good chance that you're not met or seen some of the faculty in real life.
Yeah, right. Yeah, only just a couple.
So what's the news? The COVID is going to get normal. Is there expectation for normalcy? It seems like some little bit of normalcy that's coming. So hopefully it stays like that.
You know, the positivity rate has been
still
extremely low. Like the last one I saw was 0.2%.
I've not been following it, so 0.2 is less.
And that also, you know, given the fact that the mandatory testing is no longer in place, the only time someone gets tested for COVID is if they are afraid they have it or they've been exposed. So
it will automatically come.
So that's you would think that would actually bring the positivity rate up a little bit.
Oh, because only when, yeah, you're right.
Because if I'm exhibiting symptoms,
only then yeah, you're right. So it is good, that means, right? From what I understand.
that should be good data. I mean, if it wasn't if it was.
Yeah, now I think you can close. We get locked then. Yeah, go ahead.
I think now that I lost my train of thought. I said if the positivity rate goes up, react accordingly.
Yeah.
Even in my area, where we don't have the inoculation rate that Jackson County has and SIU has, they're not seeing the same kind of positivity rates.
That's good. Good. That's hopefully good.
And those are the places that were in red zone for a good part of the
during the
pandemic.
And I always try to think that in this class I should come with the mask on, but these days I forget because I never wear it. So, but this class and the 2 graduate level classes, everyone is wearing masks except I think you and me, I guess. So I think that I should, but then I just. But my undergraduate level, everyone can put it down. Like it's a reasonably good class, about 30 to 40 students. So they're all without, and they were without even before, like even when the mandate was on.
Really?
Yeah, and I never felt like I should really point them out. If it is not my. Or the homework's going. Okay, so pick up. So as I said before, I think Michael, you and Leah were not. So homework due dates are, as far as I'm concerned, all officially crossed, but you can still submit it. I'm being lenient, so do submit it. Not too late. Like I was telling, April 30th is too late, so catch up before that. April 15th is a good deadline to put where you shouldn't have anything else most probably if you miss April 15th, from my experience, there are so many things that is going to pile up anyway. You will miss it. If you cannot make it by April 15th, you probably cannot make it back. Or at least the quality will come down afterwards because then you start seeing the deadline much clearly. There will be other things to be involved in. Okay. So. So there's a homework 9 is this. Yeah, this thing, I think the last time I did not have it with me. So the exam is on Friday. And I was saying that usually it is not convenient to move it around. You guys said Thursday and Friday, you have an exam, but study ahead of time. That's it. Best.
This is the whole from the beginning or just
Yeah, it will be the whole with midterm 3 to the end. Whatever we studied between midterm 3 and the end getting more weightage. By more weightage, typically, I mean, let's say 60% or something, or even make it 50% of midterm 3 to end and 40% from any, something like that. That's not a strict distribution, something of that sort. So it is cumulative.
from midterm 2 to end?
Yes, did I say midterm 3? Yeah, because the other course I have 3 midterm. Yeah, midterm. For the last midterm to the end gets more weightage than everywhere, but it is cumulative. So for example, if it's a 2-hour exam, so I can ask about 6 questions or so probably. And let's say 1 question from before midterm, 1 question from midterm 1 to midterm 2, and 4 questions from this midterm 2 to end of. That could be a distribution. Does that help? But that means, I mean, it could be 2 or 3 questions from before and 3, something like that. More weightage towards after. Any other questions? Yeah, so we introduced the Kepler problem, discussed a lot of intuitive concepts related to the Kepler problem. And now let's try to get the equation of an Kepler orbit. This should be an ellipse, and let's try to do that. And yeah, I think we will get the equation of the ellipse when we reach there. We should know what to get right. We should know what the equation of the ellipse. We'll talk about it when we are there. So let's introduce the problem. Oh, this is writing very well. I got some questions, so I can use them. And by Kepler problem, it also means hydrogen atom is also pretty much Kepler problem, except until you quantize. The quantization part of the Kepler problem is different, but this mostly it has same equations that is governing it, except at the end when you put in the uncertainty relation. Okay, so we said there is 2 masses, M1 and M2. There is a R1 position vector for this. Let's see, R2 and R2 minus R1 will be this. Did I make this 2 and that 1 earlier? But it doesn't matter, I don't say which one is heavier. Right? So these are two arbitrary masses. And interaction between them is governed by the interaction energy, potential energy is G M1, M2 over R. The negative sign makes it show that it is attractive, it comes towards each other. The Lagrangian of the code, Lagrangian, depends on the three positions of the first mass, the three positions of the second mass, the velocity of the first mass, velocity of the second mass, and maybe time, but it will turn out that there is no time dependence. And it is kinetic energy, the first mass, so it's half m r1 by dt square plus half m2 and the velocity square. And minus the potential energy, that's the Lagrangian, so minus makes it plus. This is G M1, M2. I was not very clear here. This should be R1 minus R2 divided by R1 minus R2. That's your equation. There is no explicit dependence on time on the right side. So we immediately say that this doesn't exist. It's not there. In this particular configuration, the time dependence is not there. We then made the substitution. We recognize that, oh, center of mass type could be a nice choice to make. If you go and sit on the center of mass, like the whole system moves, think of solar system. So solar system as a whole is moving around the galaxy. So there is one point where the center of the galaxy is exerting the force, and that turns out to be the center of mass for our scenario. And the other coordinate you could choose is the relative difference between them. So that's your two coordinates, and so in this in terms of these two new coordinates we showed last time, that our Lagrangian becomes, so this is a new Lagrangian, it's a transformed Lagrangian in principle L prime, I should say, but I'm not going to change the letter for L. So this is now R, vector R. In principle, it should depend on the R by dt, or R itself. Let's look at it for this. And then there is relative coordinates and the relative velocity. And we already got rid of time, so that's now this one. And we showed that this is half capital M being M1 plus M2. And this is the velocity of the center of mass. Plus, it turns out there is another mass you can define. This is called the reduced mass. And equations take the form. Kinetic energy of the reduced mass, and this remains plus G M1 M2 over now R, like magnitude of the vector R. Maybe I can specify it better. Notice that this does not depend on the vector R. It does not depend on the position R at all. It only depends on the velocity of the center of mass. So this is no more there. And we know that if there is no dependence on the position, that means the potential energy, there won't be any force acting corresponding to this R. So just to clarify that better, so let's write down Euler-Lagrange equations for, also there are two variables, right? For Euler-Lagrange equations for R will be vector R. So d by dt, so first we do the L by the R dot, right? So let me say velocity. So we'll define. This is velocity is dr by dt, and small velocity is relative velocity if you want. Dt. So capital P if you want, which is the momentum associated with this coordinate, will be dl by the velocity, the capital velocity. That's equal to, so that's your v here. So that's m times v itself. What's the Euler-Lagrange equations? So then you do d by dt of mv is equal to the gradient, the position derivative of the Lagrangian, but there is no position dependence at all. This is equal to 0. Okay. Because it's maybe I should write that down once more. So it is d by dr of the Lagrangian, which is exactly equal to 0. So that's all that comes about. Do for relative position also, we define momentum P, is all momentum. So that's this time mu. So this is dl by small velocity. This is mu times velocity, and that's all. And then our equations become d by dt of mu times vector velocity v. This is not even second derivative of capital R. And now we have to take the gradient with respect to R. And so let me write this as a gradient of G M1 and 2 over the magnitude R. So that's minus G M1 and 2 over R squared times the gradient of R, which is R hat. R hat. Which is of course the Newton's equation for the relative position of the two masses. Correct. So that should not be new. We could have immediately written this all the way, except that it wouldn't have been very obvious why it is mu, right? Or why the mu is coming, that wouldn't have been very obvious. But otherwise, even though it's a two-body problem, it is being governed by the first the Newton's law itself, except for this additional feature that we have this to be 0, right? The change in the velocity of the center of mass is 0. At this stage, you could say that so the conclusion is that V is a constant. V is a constant. So the center of mass moves with a constant velocity, just drifts along if there is no external. So we're saying galaxy is not really exerting a force on it. If it is just sun and earth, they just drift with whatever the initial velocity is. We can choose our frame to be attached to this, having the same velocity as this. So choose. So let us choose simplicity, or doesn't know there's no generalization. I mean, you don't lose any generality at all. Let's choose B to be equal to 0. It's a constant. Let's sit on it. So it's equal to 0. What that means is that you get rid of this also. The velocity dependence is also not there. So that means that now the Lagrangian, oops, it didn't move it. So what that means is that the Lagrangian now depends only on R and the velocity V, and it's dr by t. That's equal. So we have chosen this to be 0. So this velocity is 0. So that's just 1 by 2 mu e r by dt, or velocity square, let's say. It's kinetic energy. So that's velocity, small velocity square, plus g m1 m2 over r, the magnitude of the vector. As I said, the reduced mass mu is 1 over m plus 1 over m2. If we have a very disproportionate two masses, let's say Earth and Sun, Sun is 1,000,000 times heavier, which will be more dominant in this interaction, in the dynamics of Earth, which will be more dominant. Okay. One would think it is the Sun, correct? Yes, the force is, remember, this is coming with the kinetic energy, right? Kinetic energy has the mu part in it. The dynamics of the kinetic energy is mainly the Earth, right? So, and how do you see that? If M1, if one was Sun and one was Earth, this is the denominator. Think of parallel circuits. Parallel resistances also have the same property. If you add inverses of the quantity, the inverse of mu will always be less than the smaller of this. So 1 over mu is dominated by the smaller ones. So Sun goes away. If you were to do this addition, Sun doesn't contribute. So kinetic energy, so the dynamics is mostly governed by the Earth. But what you could do is, so this is typically done when you do quantum mechanics that contribute. So you would like to say that, okay, what if you, like when we were doing this, writing this equation, and naively you said, okay, this is actually the mass of the electron. That's what you would have done. We had tried to immediately do it. So what is the error you make, right? So then you would say, okay, so this is the mass less, let's say, right? This is mass less. That's what you were trying to do. But this is actually mass greater is also there. So you say that, okay, I want to see how much error I make. M less, so this is 1 plus M less over M greater, right? This is a number small, right, compared to 1. So the error you make is the error probably you make is in the order of M less over M greater. For Earth mass system, this is about 10 raised to minus 6. So it's only going to contribute in the 6th decimal. So unless in that calculation there is a number coming right in front of it, which is 10 raised to 6, then you can beat that. But typically you don't get those numbers. Like it's very odd to think that there will be a number in here, which will be very possible. Yeah, dimensionless number. That's what I mean. Yeah.
Just for the kinetic energy.
In general, for dynamics, it is Earth that dominates. If you talk about the force, yes, the magnitude of the force, but dynamics depends on the how much kinetic energy and potential energy is being transferred between each other, and in that it is the lighter mass that plays a bigger role.
Potential energy Sun is more than.
That depends on the whole quantity, right? That we have to compare the two. There it is, G comes in, there's a lot of other features comes in. But I'm saying in the dynamics, like as far as motion is concerned, not just because it's a kinetic energy, this plays a lesser role because this equation, notice, this is mu, right? I can replace this mu with electron, I'm saying, and I'm good. That's the dominant feature. This mu is dominated by the lighter mass. I think that's all I'm trying to say, to be very precise. That's what I'm saying. I don't like the rest of it. I'm putting in my own intuition that dynamics is governed by that. That's probably a loose statement. Let me make it more precise. The mu here is dominated by the smaller mass, whatever that contributes to. That's a way to put it, if you really want to think about that. Okay. Helps. Yeah, like the question one asked typically is that when you do the corresponding thing in hydrogen atom, you say that if you were to provide this in, you first do the calculation with m electron, and that is what your Bohr's orbit has. Then you say that, okay, what if I change this? What if I include the mass of the nucleus also in the hydrogen atom? Then what's the correction in the ground state energy? Like that's a standard question you address in there. And there it comes out, I think, if I remember right, within the third significant digit. It's not in the sixth significant digit. There, yeah, there, because it is 1,000 times, 2,000 times small, right? Mass of the proton is 2,000 times heavier than mass of electron, so it's probably contributing to the second or third digit there. Yeah, I think that's all. Okay, so with that comment, let me proceed. So now we have made little progress. We had earlier 6 coordinates to deal with. Now we have 3 coordinates and 3 phase or 3 velocity coordinates also, but we still can make this simpler a little. And for that, we say that we immediately notice that this is only dependent on the length, right? The distance between the 2 masses. That seems to suggest that if you were sitting, or even if you were having a center of mass somewhere here, it seems like it doesn't matter in what orientation it is, whether it is facing the North Star or is it facing, is there a South Star? I don't know. Yeah. What is the North Star, by the way? What's the relevance of the North Star? You know, there is a star called North Star. What's the relevance of the North Star? What's the property of North Star?
It's the brightest. No, there's a move in the sky.
Exactly. Like if you look at it, every star actually rises from the east and sets in the west. There is one star just doesn't move. If it was dark in the day, it will still be there. And that's because, I mean, there is an axis of rotation, right? So we are rotating about an axis. Everything here, it goes down. Like if there's a star here, goes in, comes back. That's the motion. But what if the star was right there? That's not star. It's pointing in that direction. So it doesn't move at all. Right? There is a star in the sky, it just doesn't move. It's not the brightest. And you can use that for movement because that will stay all the time the same. So if you move around, if you are lost, you just have to search for that. But in the morning, it's not there. That's the point, and we usually travel there. But the question, and there happens to be a star there, it doesn't have to be there. But it's nice that to a good approximation within that region, there is a star there, so we're lucky, and it's reasonably bright, so it's always visible kind of. And but the question is there a star down in the star in the south? There's the other side of the axis also, right? Quiz, right? Find out if there is a star at the other end of the axis, which is reasonably, I'm sure there is a star, but is there a bright enough star? I think that's like typically within some angular distance of 1 degree, you can always find the star. Okay, so why did I bring that up? Yeah, so I was saying it doesn't matter whether you are having, so currently we don't have the North Star, right? That is, the universe is empty, there is only 2 masses. And does it matter whether you orient it like this? Still it is R1 minus R2, whether you orient it that way, it's R1 minus R2. The orientation doesn't really matter. So there's an angle independence in here. And based on symmetry principles, we know that whenever the angle difference is not there, probably angular momentum is conserved. Right? So we investigate that. Let's talk about angular momentum, right? So L is R crossed with P, where P now is a canonical momentum, that's mu times V, right? So this is equal to mu times R crossed with R by dt. So that's your angular momentum. If we want to see, we want to check whether this is really constant or not, because there seems to be angle dependence in this potential and in turn in the kinetic energy. So let's check that. So what we do is just do time derivative of that. You can do Poisson bracket also. If you do Poisson bracket of L under rotations of L, that's another way of looking at it, but I didn't go through it too much in detail. So let's just do the simple way that you do the time derivative of L. So that's two of them. So R and this. So it is mu times dr by dt. You can have two derivatives, right? Either here or there. It's crossed with r by dt plus mu times r crossed with the second derivative of r with respect to dt square. That's mu v cross v plus mu times r crossed with second derivative of r, so even mu can be taken is minus of this, right? So minus of r hat. And then there is g m1 m2. That's using Newton's law. Correct. What's the cross product of two vectors? 0, right? Is it always 0? P cross V? If it's the same vector, is there, under what situation is the cross product of two vectors not 0? I think I might have said this before. You see this in your homework if you've done the Poisson bracket homework. The magnetic field. There you do the commutation relation of V and V. Quantum, if you're doing quantum mechanics, angular momentum L cross L, right, is not 0. Like cross product has usually a one-to-one correspondence with commutation relations because it is in the L1, L2 minus of L2 minus L1. So if we are doing quantum, or if they were operators, then V cross V need not be 0. So that means to say that then you should address this. Oh, what if you do the same problem in quantum mechanics? Is angular momentum conserved in quantum mechanics? Is angular momentum conserved in hydrogen atom? Yes, no? Yes, right. So yeah, so even though this is there, even then angular momentum is conserved, but it's not because of this. This cannot be immediately, it's not 0, but then this is positions, so you have to be careful, but that doesn't mean that it need not be 0 either. Not every cross product needs to be 0. So, but in this case, we do have this to be 0, and this is vector r crossed with r hat. That's also 0, right? I can write this as r over r cubed, for example. That's also 0. That's 0, and that's equal to 0. So L is conserved. So L is conserved, that means L is a constant. L is fixed or constant, right? L is equal to a constant. Let's see. Yeah, L is fixed. L is constant. What can I say about R dotted with L in that case? R dotted with L. R, remember, is the position of the particle, and it is a time dependent quantity. R dotted with L is R cross P. So it's R dotted with R cross P. That's the same as I can, in this cross and the dot can be replaced. So this is R cross R dot P. That's also, and that's 0 because R cross R is 0 again. So it seems, right, if L is a constant, then every position has to be perpendicular to L. So the position, so if you have a fixed L, so this is your L, and the position of the particle always has to be perpendicular to this. That's your R. So it seems like it picks a plane. Since it's a time-dependent quantity, it picks a plane. So it seems like it is convenient to choose. So let L be equal to, since it's a constant, I'll pick it in the z direction. Let me choose L to be LZ. So this is a choice. And then the vector R is in a plane, so z coordinate, so z hat dotted with R, which is basically just z, right? Z can be chosen to be 0 again. This can be chosen, so, or at least the motion is, there is nothing interesting in that motion. So it seems like vector R can be just x and y. Xi hat plus yj hat, or you can have the radius R times R hat plus just R times R hat, I suppose. Or as far as coordinates go, I can have R and phi. The cylindrical coordinates on a plane, I can work with R and phi. Notice what are the things that went by. In general, there are 6 coordinates possible. You went to the center of mass frame. Physically speaking, you went and sat on the center of mass frame. That got rid of some of the variables. Then we are saying that angular momentum is conserved. You choose your angular momentum to be along the z direction. So now your motion is fixed on a plane. So you have only 2 coordinates to worry about now, R and phi. So this Lagrangian then depends only on R and phi and the velocities corresponding to it. So 2 coordinates and the velocities corresponding to that. So that then brings down the Lagrangian to the following form. So L, which is R now, and there is an angle phi, and there is a distance. This is the velocity, the radial velocity. And then there is a tangential velocity, which we call the angular velocity, right? d phi by dt. That's the quantity that this can depend on. What about the kinetic energy in that case is 1/2 times mu r dot square. R dot means time derivative of square. And the angular kinetic energy is 1/2 mu r square phi dot square. I think you've done this sufficiently, I can directly write that. And that's the kinetic energy, and your potential energy is minus of G m1 m2 over R. So we started with 6 coordinates, now we are down to 2. And then the idea is that phi will serve as time for us in a sense. And so it is pretty much 1 variable problem. But as of now, it is a 2 variable problem. Okay, so now we have 2. So again, let's write the equations. This time in terms of these 2 coordinates. Earlier we wrote down our equations, but in terms of the vector R as a whole, correct? And then we got a vector equation now. Now we are going to write our equation for the radial velocity, so radial coordinate. Right? So let's do this is a Lagrangian. As far as it's Lagrangian, Euler-Lagrange equation holds, and we again let's do P of R, right? P of R, the canonical momentum for the radial coordinate is dl by dr dot. That's equal to mu times R dot. So my Euler-Lagrange equation is d by dt, so it is mu times R double dot is equal to, now I have to take the position derivative or with respect to r for this whole Lagrangian. And then we realize that there are two places where it hits. So it is mu times r, right? So it's just mu times r times phi dot square. And it can hit here also. So that's minus of g m1 m2 over r square. So it seems like there is an additional piece here. What is this? Can you associate this with something that you see in undergraduate physics? What is this term? What would you name this? This is a force, right? This is mass times acceleration. Centripetal, or this time you might call it centrifugal, maybe, because it's in the positive direction. But this is what is usually called the centrifugal force, right? M/r omega squared. Good. So let's now next do the phi. So phi will be angular. This is the canonical momentum associated with the angle phi. So that's equal to dl by d phi dot. And that's equal to, so there's only one place that shows up. So it is mu r squared times phi dot. And the equation then becomes d by dt of the momentum, but notice that there is an r there, so I should not just write phi double dot. So it is mu r squared phi dot. And what is that equal to? What is that equal to? 0, right? It is 0 because there is no phi dependence in there, there is no angle dependence in there. So that's equal to 0. And that immediately says that that's equal to a constant. It turns out that that is exactly the same constant I used here, but let me not, that's not very obvious that that is the LZ. So that should be left as an exercise that shows that that is actually the angular momentum itself. But for now, think of this as some LZ prime, right? Because we don't know, but it is exactly the same thing, so that I can use my LC here. Right? So that's the angular momentum. So the moment, this is a constant that immediately tells that I can fix that as a constant. So that's L mu r squared phi dot is equal to LZ. That's my choice. And that's the connection you have between phi and t. So we learned that d phi by dt is equal to LZ over mu r squared. And more clearly, the change in angle, or let me write this as, let me write d phi is equal to LZ over mu r squared times dt, or dt is equal to mu r squared times LZ times d phi. Not necessarily a uniform scale, but a change in angle decides your change in time, or change in time decides your change in angle. So in this sense, angle can be used as a time coordinate for our purposes. Okay, so if that's the case, if you can replace it, we do see d phi by dt in here. So let's go ahead, and we would like to change all the time coordinate, but for now, just let's change the phi coordinate in there. So we have, I'm going to this equation now, mu r dot r double dot. So second derivative, this is your equation of motion for the radial coordinate, how far you're going off, or what's the distance between the two masses, how does that change with time? So it is mu times r. Phi dot we said is this, so this is LZ over mu r squared, and that's the whole square. Minus g m1 m2 over r squared. This is your equation for the rate at which the radial coordinate is changing. I would like to see this as a change in energy. Energy is conserved, or we expect the energy to be conserved in this case, because potential energy, this has a potential energy associated with it. From other contexts, we know that. So we expect energy to be conserved, or we can say it is time independent, right? The Lagrangian is time independent. That's the reason why we expect energy to be conserved. But then what is energy, right? We would like to know where is that energy. So let's write this as a total time derivative. Is that possible or not? So for that purpose, so let's write this as this is dy dt of mu times r dot. So that's no, let's not do that. Sorry, it's not the way I want to do. Actually, yeah, let's multiply by r dot. So let me multiply by r dot to this equation. So that's mu times velocity times derivative of velocity, right? So it's d by dt of r dot. Velocity times derivative of velocity. That should give you an idea that this is like kinetic energy. You've seen this trick before. That's half of velocity squared. When I multiply by r dot, so what is happening here? So this is dr by dt times this is Lz squared. One of the mu cancels. There is an r raised to 4, so that's mu r cubed. And this is minus dr by dt of gm1 m2 over r squared. I want to see this as a total time derivative. So for that purpose, I write this is d by dt of half mu r dot square. That's your kinetic energy associated with the radial change in radial coordinate alone. This is not the total kinetic energy. That shouldn't be confused at all. Let's write this as dr by dt times a partial derivative of something, partial derivative with respect to position. So this is an r cubed. Notice that partial derivative of r squared gives me a 1 over r cubed. Right? Except that this gives you minus 1 by 2, so this should be minus 1 by 2. Right? So derivative of r squared is minus 2 over r cubed. And that's that feature that comes in. So let me write that in here. So this is minus 1 by 2 r squared. Right? So this is minus 1 by 2. So it's Lz squared over 2 mu r squared. Currently just manipulating it and trying to get a total time derivative of, because dr will cancel here. And let's write this also in that form. d by dr of 1 over r is 1 over r squared with a minus sign. So I write that here. So minus 1 over square is, so it is plus. Right? So it's plus g m1 m2 over r. And you recognize that as your potential energy. So that r depends on time. That's the only coordinate it depends on. That is the one dependence quantity. So these two can cancel out. That's a chain rule. So we learn that d by dt of 1 by 2 mu r dot square plus Lz square over 2 mu r square minus g m1 m2 over r is equal to 0. Which means that that's a constant. And you recognize that, oh, that's a potential energy that's sitting in the dimensions of energy. So this must be the energy, or we can define this to be a constant. We'll call this that, right? And it has all the properties of energy. So, okay. Any questions until this stage? So let's proceed further. And so we are going to call this energy, so it's E. E is fixed. And it has a kinetic energy associated. This is not the real kinetic energy, notice. Kinetic energy has a radial component, and so that's your kinetic energy. Where is that? Yeah, this is your kinetic energy, right? This is your total kinetic energy. This plus this. Right? This is not really the kinetic energy, it's part of it, like only the radial velocity. But now we are going to call that K, and there is two more p's to this. So this is LZ square times 2 mu r square minus of G m1 m2 over r. So that since there is r dependence in here, it's very convenient to say that this is an effective potential energy. In this problem, if you think of this as a kinetic energy, this is not the kinetic energy of the particle, this is the kinetic energy in the radial direction if you want. So that's your KR if you want. And that's the effective potential energy that decides your motion only in the R direction. If you were to think of this potential energy, immediately you want to draw it, right? That's what decides your dynamics mostly. Like if you know the shape of valleys and mountains in a region, you know exactly where a ball will go and rest, right? It will go to the extreme bottom of the valley. So potential energy has exactly that. Meaning, how does this look like? At the far distance, it is negative. At the far, very large R, this dominates, right? Because 1 over r squared is really tiny. For a very large distance, r equal to infinity, this dominates, it's negative, so, and it goes to 0, right? So somewhere here, if I were to, I'm plotting R with U effective. The effective potential energy for the radial direction. It seems to be dominated by the second term here for large R. What about small r? When r is small, 1 over r squared dominates. So this is not there, and it is positive. So for very large, small r, it is somewhere here. And when r is 0, that goes to infinity, right? So very, very small r, it is going up to infinity. For very large r, it is negative and going to 0. Only way you can patch it up is that at least there is one place where it goes to a minimum, right? It must be something like this. Might be. There might be more than one. We don't know. So then it raises the immediate question that if there are minimal points in here, right, what is this point or not? And if there is that minimum point, that brings in an energy scale also. What is this U naught? So that's very good to know. And how will we find that R naught? Derivative of this effective potential, right? So let's take the derivative of U effective with respect to R, and we want to set that to 0, right? Oops. So that should be, so that's R squared, so it is minus, right? So minus LZ squared over, as a 2 cancels out, so it is mu R cube. Minus becomes a plus when we take the derivative, so it's G M1 M2 over R squared. Whenever this goes to 0, I will call that R naught, right? That's what I have called it, R naught. So let me call it R naught, and I'm setting that to 0. And it seems like there is one solution. There's only one solution because it's R cubed, but most of it is in the denominator. In the numerator, there's only one R naught. So this seems to be governed by help. So this is LZ square over mu, and this is positive, equal to G M1, M2, and R naught. Right? That's when that is equal to 0. So R naught is equal to LZ square over mu times G M1 and 2. That's a characteristic parameter of an orbit of any particle, whether it's a meteorite or Earth or any planet. That plays an important role. That's a scale in the distance, if you want. Always that is a scale everywhere here. You have a scale in distance and there is a scale in energy, right? So that plays an important role. The final place when we really write the equation of an ellipse, that R naught will stay there. So that's your R naught. And then immediately you ask, what about the energy? What about U naught, right? What's the energy right at this bottom point? So U naught is equal to, go back in here, LZ square 2 mu R naught square minus G M1 M2 over R naught. Multiply by an R naught, divide by R naught, and you learn that. So this, yeah, one of this is LV, right? So this is L's of LV square over 2 mu R naught square. Or actually, I want to replace LV with that. So LZ over mu is GM1M2 times R, right? So this is 1 by 2 times GM1M2 over R naught. And this is minus of GM1M2 over R naught. That's equal to exactly half of the potential energy at that particular point. So at this, whenever the planet is at this position, it has a potential energy. It doesn't having this half. So divide that by 2, and that's your effective potential energy. Where effective potential energy is getting contribution from the angular motion also. So that now we know U naught, right? So these 2 points are important. Right? So okay, so we want to do something more than this, a little bit more analysis here before we go and find the equations. We have an energy. Let's rewrite this first of all in terms of these coordinates. Right, there are too many parameters there. So let's at least that before we discuss the physics of this. Yeah, energy. I think all this is done. Taken care of. Okay. So let's do something. Let's rewrite. Energy is constant, right? Energy is conserved. Energy is constant. Let's rewrite this in terms of these quantities. So we have energy is equal to 1 by 2 dr by dt. Let me write that as d phi by dt times dr by d phi. Because d phi by dt is given in terms of angular momentum. So that's just a way of writing it. Plus LZ square over 2 mu. LZ square over 2 mu. I provide an R naught in there. So that means this LZ square over 2 mu R naught square. And this I write it as R naught over R square. I'm giving dimensions of energy everywhere so that there is a dimensionless parameter coming. Everything is in terms of R naught. And minus of G M1 M2 over R naught, and this is R naught over R. G M1 M2 over R naught is how much? 2 times U naught, right? We can replace that. That's also equal to, if I could have written this, yeah, here, right? So G M1 M2 over R naught is R naught squared. So this is also equal to minus 1/2 of LZ squared over mu naught, mu times R naught squared, right? That's also a possibility. So yeah, so this is equal to 1/2 times mu d phi by dt. There was a relation for what was, so it was mu r squared times d phi by dt was LZ. So d phi by dt is LZ over mu r squared. So it is LZ squared over mu squared times r raised to 4. Right? It's r squared, so it's r raised to 4 here. And this is dr by d phi squared. So rate at which radius changes with angle, that's what we will do. LZ squared over 2 mu naught r squared, so that's minus u naught. So minus u naught times r naught over r whole square. And this seems to be minus, so this is minus g, so it is 2, right? So it is plus 2 u naught times r naught over r. What else can I do? Again, search this LZ square over mu r naught squared times 2. So one of the mu's cancel out. So this is having a minus u naught times 1 over r squared. So this is r squared, r naught squared over r squared. Mostly manipulating at this point. Plus 2 u naught r naught over r. Divide by, so let me rewrite this. First of all, divide by u naught everywhere. I get an energy over u naught. And take this to the left hand side. So I have r naught squared over r squared times dr by d phi squared. That's my differential equation if you want. Did I do this correct? Yeah, I think yeah. And this is dividing by, I've taken this to the left and bring this here, so it becomes minus e over u naught. And we have minus r naught over r whole square plus 2 times r naught over r. That's it. I see a complete square there. So I add and subtract a 1 if you want. So 1 and minus 1. That's it. It's a trick. So everything is constant at this point. Minus or that's 1 minus and I can take a square root. This just helps in the next step. But before I go there, I want to analyze this. Here, let's go back to that graph we had. Like potential energy curves are very informative. So let's analyze this. So we have R naught. That R naught is equal to LZ squared over mu times G M1 M2, and U naught is minus half of 2G M1 M2 over R naught. And if you want, that's also minus half LZ squared over mu squared. Yeah, did I mess up?
I think that because you put the negative inside the binomial, the minus.
Here, oh, this should be plus, you're saying. Oh, no.
Okay.
Okay.
Well, let's see. How do you? Okay, it's okay. I was looking at the factoring the negative out of the three terms at the end, but no, that's
So
the
this-
square
Yeah,
takes care of that.
correct, yeah. I think, okay, this seems okay.
Yeah.
Like, the only thing I don't have it in my head is that I'm not sure if this is a R or not, but dimensionally, I'm seeing that's dimensionless. That's, yeah, this has a dimension of R. Yeah, there's a mess up here. Yeah, this is wrong, right? I thought this was R squared, because this is dimensionless, 1 right here. And this seems to have the dimension of distance. I missed an R somewhere. It should be R squared here. Okay. Let's see. So this is mu LZ over that's the angular momentum. So it is mu R squared phi dot is equal to LZ, right? So d phi by dt is LZ over mu R squared. So LZ square mu square R raised to 4. That's correct. When I went from here to, so let me do this, so it is one of the mu's cancel out. So it's 1 by 2 LZ square over mu times R raised to 4. And I would like to use this. Correct. Is that correct? Okay, so that's equal to 1 by 2 LZ square over, I want to write that as mu R dot square. It's R dot over R raised to 4. Right. Which means that there is R dot over R left, right? So this is equal to minus of U naught times R naught over R square, then the square. So I wrote this as U naught times R naught square over R square. It should be R raised to 4. So this should be R raised to 4 here, right? So correct this. I'm not going to erase this so that you guys can see what I'm doing. So this is R raised to 4 there. Switch this, I have not erased it, I put a circle there. Which means that when I write it here, so this is R raised to 4. This should be R raised to 4. When I take the square root, this becomes R square. That's what in my head I felt it was R square. Oh, I didn't. Yes, sorry about that. Okay. Okay, with all that, yeah, anything else? Any other comments before I do? Oh, it's 5 minutes of physics. Okay, but okay, it's kind of nice at this point. So, yeah. So we have a kinetic energy and potential energy giving to be E that is equal. And we know that this is always positive. This can be negative. Right? Potential energies can be negative, but so what we have here is that E is equal to kinetic energy, radial kinetic energy plus potential energy. But it's necessary that K has to be greater than or equal to 0. And the best it can do is come to a rest. It cannot be negative. Can kinetic energy be negative? Probably not. So that means E has to be E minus U effective has to be greater than or equal to 0. That means the energy, the best it can do is the least energy you can have for the system is U effective. So energy has to be the total energy of the system. Like this is the actual total energy of the system has to be greater than U effective. That's the best you can do. Okay. So U effective here, the possible U effective is this. It has to be energy has to be greater. So total energy, if I were to draw on the same curve, I cannot have this situation. If this is my E, that's not allowed. That's below my U effective. The minimum of U effective is this. So the first system I can consider is that's not allowed. The best I can do is this. And when it is here, what can you, if your system has this total energy, right? That means this is equal sign here, right? So energy is equal to U naught, right? So you begin by saying that energy U is equal to U naught. What's the system doing? Can it do anything else? It cannot, because kinetic energy cannot be, it has to be 0. So, but this is not kinetic energy, this is a radial kinetic energy 0. What kind of motion is that in planetary motion? So the system is just here, it's just sitting here. It doesn't do anything. A planet, it just sits here. What kind of motion is that?
Spinning.
No. Remember, this is just R. It's
Around this.
a circular motion. It's going around, but it's fixed R. R is equal to R naught, but kinetic energy with respect to R is 0. That means it is not moving away from R naught, right? But it's still going around, right? So that's a circle. Right? This is a circular motion. So circle E is a solution for Kepler problem. Right? It's just that it's very rare. So circle E is a solution. Make the energy a little higher, right? So now I said that, okay, energy is a little higher. So energy is greater than U naught, but it's less than 0. Okay? You're not reached 0 yet. So that's your 0, right? This is 0. Now, if you were to think of it, there is a minimal radius. So remember, this is radius. It's not this is the orbit, but this is a radius. There is a minimum radius, there's a maximum radius. And it need not be the same. That reminds you of an ellipse. Right? Minimum radius, maximum radius. This is elliptic orbit. And that's what we will do. We'll get an equation for this next time. We are almost there. We can solve this and we will get, this is just one substitution. We will get that. But it seems like we can still go further, right? What if you have exact this motion? If E was exactly 0. The elliptic motion is very common, we understand that, right? Right? But now you are having this as your energy, you start from here, there's a minimum radius, right? And then it comes down and then goes all the way to infinity. Right? What kind of orbit is that?
Hyperbolic.
No. It is, okay, maybe I should first discuss this. Hyperbolic is this, correct? You start from here and you go all the way to infinity. But in between that hyperbola and an ellipse, there is one more, which is E is equal to 0, very special. Right? So this is just to, if this is E greater than 0, that's hyperbolic. What other is a possibility? Circle is a possibility, we know. Hyperbolic, elliptic, what else in conic sections? Remember your conic section? Is that clear what I mean by conic section? Take a cone and you cut out things. There is one more curve that is possible. Parabola, right? That's parabola. Good, right? So that's your motions and that's your paragraph. We won't be able to cover all of this. Each one of this should be covered. Mostly it's the same, but it's a good analysis to make. We will talk about elliptic motions and where all these points are, like this point, what does that correspond to? What does this correspond to? So those kind of simple physics coming out of these equations, and why is this an ellipse? What's the orbit of an, what's the equation of an ellipse? And simple things which you've seen it here and there, but everything connected from this equation is nice to know that oh, everything is so fitting in so nicely. So we'll do that. And using the same equation that on Thursday, next Thursday, we'll do a perturbation and get how the perihelion moves. Perihelion is this point, the maximum point. Right? One is perihelion and one is the lower one. Perihelion and epihelion. So, yeah, we'll come